name is Elham Mirzaei, and I'm working for InSystems Automation. We are specialized in developing innovative solutions for intralogistics specifically. I would like to go with I would like to start about our domain of industry that we are involved. So basically, as I said, we are providing solutions in logistics industry, which means we are focusing on transporting goods in warehousing or specifically in the factories. And the challenges that we have, like rapid change of market and also the ability of the system to cope with quick, fast production reconfiguration in a complex setup, or rapid demands or high demands in the batch size one production, necessitates for us to go for new solutions and go higher than the level of automation. I would like to here explain how we are evoluting our systems in a way to bring more AI application to our infrastructure. So basically, just a short summary of automation that revolutionized the intralogistic industry, comparing to the conveyor belts that was already there, which provides the fixed material flows only between 2 points. By replacing all those conveyor belts with transport robot or AGV, automated guided vehicles, basically the problem of space, the problem of space solved, and also, more importantly, it provides flexible material flow, meaning that the materials can be flowed, can be transported between any different points in a flexible way. This also increases, of course, the productivity, the efficiency of the system, and also the problem of safety, as transporting these heavy goods is obviously difficult for a human. So this is an introduction how automation comes and revolutionized this industry. As I mentioned, InSystems is providing these solutions since 2012, and we are providing cooperative systems, which means that our robots are able to share space with humans. So basically, they are certified to work with humans. But here is an overview of our different kinds of AGVs. We have different types of AGVs, depends on the capacity load the customer needs to load or unload, between 30 kilograms and 1,200 kilograms, basically. And as we can see, there are different types of conveyors based on the objects that they can handle and they can move and transport. The key features of our system is natural navigation, meaning that our systems are able to make the path plan without any reflectors or any marks on the ground. So basically, every robot is making and planning its optimal path to drive toward the destination based on its local map. But since 2018, we are involved in some kind of research and development projects, and as a result of that, we go to the higher level and we bring our system to the level of collaborative systems. Which basically I would like to explain what does it mean. So consider a collaborative system. The first transition of cooperative system to collaborative systems comes from the fact that we need to remove our centralized fleet management, meaning that we have to bring more intelligence to our system to be able to handle a couple of functions or main functions that our central unit was before doing that. Some kind of plug and play at runtime, meaning that imagine in a fleet of robots, a new robot is added only by switching on, and it can easily get information from other agents in the fleet and be a member of fleet easily without human interfering. And the most challenging part of this decentralized fleet of AGVs was the distribution of job assignment. Because before, our central unit was sending all the orders to the robots, so that each robot just basically receives the orders and tries to perform the task, perform the transport. But by removing this central unit, then this challenge comes that how this job assignment distribution should be done among the systems, among the robots. Basically, the requirement, the first step to, and the first requirement to make this infrastructure was to add a communication layer, communication framework to our system to basically form an adaptive IoT system group, which can easily change between different members of the groups, either any AGVs or any production units, or even though the stations, the load unload stations or charger stations. So this was the first step. We already started, and we somehow go through the collaborative IoT scenario, which, as I mentioned, was the basic challenge for us, job distribution. Imagine that there is a fleet of robots performing in a factory, and the machine execution system is taking the orders from any production units. Basically, one production unit is asking or requesting for good transportation between two stations, and the robots are able to negotiate about which one is the best option to do this job, to do this transportation. For example, here you can see the job comes and the robots are sharing the data of their cost to do this transport, and basically the robot who has the minimum cost will win the job and will perform the job. To have such a, to be able to cope with this challenge and have such a functionality, we had to bring new CAC, which is collaborative AGV controller logic, on top of our system to be able to handle such a situation, do the negotiation, and removing our central unit means that we have to cope with multi-level goals, which means that the robots need to fulfill not only their individual goals, like always take care of your battery, for example, but also the global goals of the fleet. So to fulfilling the jobs in a efficient way to increase the productivity of the whole system. So the first questions in this scenario of negotiation of over the jobs, the first question that comes is, who will win the job? Who will win the bidding? And to answer this question, I would like to highlight here how does this system work. So basically, the requirements come from the plant manager. For example, the plant manager just determines its goal, its requirement, which is that I would like all the orders that come into the factory be done as soon as possible. So this will be modelized and formalized as system goals, as I mentioned, at different levels, locally and globally. Here, the local goals is that the robot, each individual robot, should take care of the battery health. As you know, the lithium-ion batteries, which is used in these AGVs, they need some kind of observation how to the usage of these batteries. So this is the local goals for this system, for this requirements. The global goal is, as I mentioned, the requirement that plant manager defined here. So based on that, we formalized some kind of cost function. So that the robots referring to this cost function can calculate whether it is the winner or not, or the other robots. So after defining this cost function, we need some kind to define correspondent KPIs so that we have the feedbacks if this strategy, if this bidding function is working well or not. Getting back to the decentralized and centralized transition, I would like to highlight that by removing this central unit, robots should be able to define some kind of strategy themselves to do all the jobs, all the instructions that the central unit was doing. So we need to define some kind of strategy for the whole behavior of the fleet individually and globally. And this is how it's done for the job assignment in the bidding strategy and in the cost function model. So basically, the bidding is done based on this cost function. The robot will exchange the data of the parameters that are important or highlighted dependent on the strategy. For example, if the strategy is as soon as possible the jobs should be done, definitely the distance between the robot and the destination that it should load, it should transport the goods is really important. So the robot who is basically nearer to the station should win the job. But this is one of the parameters. As I mentioned, it's a difficult and complex formula to consider different aspects, different parameters, and correspondingly activated those parameters in the cost function and consider that in the cost function. After the winner is determined by the robot themselves, the robot who wins the job basically just adds the jobs to its local queue and starts performing the jobs basically from top to down according to the number of jobs that it has. But meanwhile, the robot should be able to participate, to predict some values. For example, if it needs to charge before doing this transportation or not. And by considering all these aspects, it should be able to give some or publish some realistic cost function, which is reliable. So basically, the job will be done this way. Another challenge is considering the fleet, we have one station that should be shared among different robots, transporting different goods as different jobs. And while two robots are winning two different jobs, how could they remove the conflict of driving both of them to the station? This was also another challenge we had to consider for addressing this problem and making solution. We kind of using the token approach, which means that every robot, before starting to driving toward the destination or toward the load station, it needs to ask for some kind of permission of or some kind of status of the load station. Either it is occupied or free. If it is free, it can easily drive to, or if it is occupied, it has to wait. But the waiting spot somehow is defined in a nearest spot to the station, so that the next robot that comes and waits in the waiting spot can easily pass the token from the previous robot and just go to the station and load. And here, once again, negotiation comes into play in this way, so that imagine that two robots have the same shared station, needs to load different goods there. So basically, we should define also some kind of priority, which means that if the robots with a basic good, which is important for the more important for the production line, needs to do this transportation first, it should do the negotiation once again here with the robot who already has the token and ask for the token to do the jobs before that. And the other robot will go to the waiting spot and wait for the first robot to do the job. In order to be able to validate such a system and to develop some kind of simulation, basically we simulate our physical behavior of system, the navigation, the fine post, and the whole system path plan, including the CAC logic also on top of that, on ROS operating system, which is the robotic operating system. And this gives us the opportunity to validate our logic before we deploy it to the system, and also have kind of combination of real virtuality system, because our real system also is based on robotic operating system, ROS, which make it easy to transit from the simulation to the real systems. Here is the simulation of, so the video is not playing, but I don't know. Unfortunately, the video is not working, because here I had the scenario of including two strategies and see how the job distribution is done. Yeah, okay, I will skip it. But currently, after providing this infrastructure and enabling our system to communicate and have all this negotiation, we already go to the next step, which is self-organized and self-optimized systems by using the general AI. Here, the general, I forgot to mention that before in the past stage, the narrow AI was used. So the goal is that use the data of the whole fleet and the whole production lines, and based on that, both the real time and also the static data, based on that, the robots should be able to have some kind of predictive, for example, for the peak time of the factory. Imagine that robots is able to predict that at 10 a.m. on Monday, the whole fleet should be prepared, which means that all the robots should charge to 100% to be able to handle such a peak time for the fleet. To achieve such a system, we need to use big data and also add some kind of methods of deep learning, and be able to optimize the workflow and performance of the fleet by adapting the recurring patterns in the work cycle and the production line. This somehow is successful because in most of the factories, these production lines are mostly repetitive, so that we can easily find out and bring some kind of or recognize the pattern, and the robot is able to change the strategy to cope the needs of the system in a dynamic way, based on the changes either to the systems or to the environment. For example, if a dynamic obstacle appeared somewhere and the path is blocked, this information is passed is distributed among all the robots, and all the robots tries to consider this in their bidding function and tries to optimize themselves to keep the productivity of the whole fleet. So this level is the self-organized and self-optimizing systems, which is currently under development, and we are trying to validate and test our system both on our real robot and our simulated systems. For us, the next step is to, as I mentioned, validate such a system, being able to make decision and being able to change its behavior without any central unit according to the need of the machine execution system and according to the changing environment. And also mixed reality technology, as I mentioned, and autonomously working devices generate their own return of interest, which means that at the end we would like to have our system as a service, so that any people can just order such a service and use it independently where it used, of course, internally. Yeah, thank you for your attention.